Our summit begins today with a presentation from Mike Czarick. We move there with a presentation from Michael Coles, one of our product managers, regarding innovation at Val-Co and how we're innovating in feeding and watering. That's followed by an agricultural economist named Stephen Blank, Dr. Stephen Blank from Virginia Tech. That's at lunch. Followed by Sean Francie, who's going to talk about this great new controller we have called Horizon. And then I'll be following up the day with a quick talk on a new dealer portal that we have for you all. I'm going to try to get everybody out of here around 2:45, 3 o'clock, so that we can take some time to enjoy a little bit of Lancaster, maybe have some downtime. But then we need everybody back here in the lobby at 6 o'clock so that we can load ourselves in buses and head up to Lomont Farms for an experience we're calling Americana Jubilee. At this time, I would like to welcome Mike Czarick. I know that many of you have probably heard Mike talk at various industry events, or perhaps even taken some of his courses and seminars at the University of Georgia. I think Mike has a very, very exciting presentation for us today. I'm hoping that you all have lots of questions for him. So without further ado, welcome, Mike.
Hopefully that worked. Yep. Okay. Well, it's my pleasure to be here with you today to talk about some of the latest insights into poultry house ventilation to optimize bird production. And really, when you look at the latest things, the biggest changes in poultry house and other species ventilation really is the hot weather ventilation. And when it comes to hot weather ventilation, it's all about airspeed. Simple as that. The more airspeed you have, the better you're going to perform. That's ventilation 101, hot weather. Turkeys, 80 degrees, 150 feet per minute. They're obviously hot, they're all panting. Take a thermal image of them, look at their feather temperature. Even though the air temperature is around 80 degrees, their feathers, their bodies are glowing, showing between 85 and 90 degrees because all that heat is building up. How to remove heat from the birds? You blow air over them. The more air you blow them, the more heat you pull off them, the more feed you can put in them. That's all there is to it. Oh yeah. Turkeys sit down when they're comfortable. The biggest problem I have with people new to tunnel ventilation is looking at those birds. They're sitting down. They're not eating. No, they're sitting down because they're comfortable. The more active the bird is, the more it's running around, the more you're losing feed conversion and performance. Turkeys sit down. Yeah, you can make them sit down if it gets too cold, but for the most part, the temperature is over about 75, 80 degrees. They sit because they're comfortable. Here's a good old naturally ventilated house. 85-degree day. Look at the feather temperature running 96 degrees. House right down the road, 600 feet per minute airspeed. Feather temperature equals to air temperature. That basically means quick and dirty. I'm pulling heat off those birds as fast as they're producing it, and they will continue to eat and it will continue to gain weight. Commercial layers, no difference. We need airspeed moving down that house, not only to get air over the birds, but to pull the heat out of the cages. The only way I can get heat out of the cages is having a high IO velocity and pull the heat out of the cages. Low IO velocity, again, they're all glowing. High velocity near the pads, big and blue. We're just blowing that heat right off of the birds. Oh, colony broilers, cage broilers, big thing overseas. 100 feet per minute, 300 feet per minute. 100, 300. See the bluing effect, pulling the heat off the birds. Floor broilers, 78 degrees, no air movement. That's the trick with a modern broiler, is that if you look at the target temperature for some of these 8-pound birds are around 50, 55 degrees if you think about it. How are you ever going to get 50, 55 degrees during the summertime? You're not. You have to have that airspeed. Here it is, 78 degrees. These things are just glowing. They take in 7 times the amount of energy that we take in. They produce 5 times the amount of heat that we do per kilogram body weight or pound body weight. 85 degree surface temperature, airspeed 300 feet per minute, 81. It's my favorite one. 85 degrees, 250 feet per minute. They were catching the birds. The catchers thought it was a wise idea to close the tunnel doors and open up the end wall door. Because if you open up the end wall door, you get a really high air velocity coming into the house, which means you have a really high air velocity going down the house. No, it means you've choked your fans down. So here they have every single fan on, trying to pull all the air through the tunnel, the end wall door, with an airspeed of 250 feet per minute. Open everything back up, drop the pressure, get the fans working right. 550 feet per minute. All we're looking at a difference here is simply getting more and more airspeed. Now, the big thing we're seeing is the size of our birds and the size of our houses to some extent has basically increased the need for having higher and higher airspeeds. And this is a lot harder than people think it is. Oh, just put in 2 more fans. No, it does not work that way. The fact of the matter is, whereas in the past 500 feet per minute was considered sufficient, that's good enough. Now, more and more companies are looking 600, 700, 800. Oh, I want 1,000 feet per minute. Guess what? You can't get it. There's laws of physics that tell you cannot get 1,000 feet per minute in a house. Oh yeah, I've got a house. No, you have a house that has a spot of 1,000 feet per minute. But you can't get some of these higher air speeds. Yeah, the birds are doing well with the 600s and 700s. But the fact of the matter is, obtaining these high air speeds is a lot more difficult and expensive than people realize. And it's a lot more than just adding a fan or 2. The right kind of fan has to be added. The right amount of pad, the right tunnel door, all of it has to be designed. And that's one of the things I'm thrilled to talk to an audience like this. You are the people that design facilities. I make suggestions. You design them. And you're the key audience I want to talk to, because hopefully I'll make it easier for you to design these houses properly and to be able to show your customers why it takes this many fans, or why it takes this type of fan as opposed to just throwing any old thing in there. So let's look at an example. What would it take to get in a broiler house, and we'll look at cage layers and other things too, what would it take to get a true average airspeed of 800 feet per minute in a broiler house? We're going to look at a house, a 50 by 560, 9.25 average ceiling height. How much fan capacity we'd need? It's pretty simple. CFM equals our design air velocity times our house cross-sectional area, how big the pipe is. We just multiply our pipe size, square feet, times our airspeed, feet per minute, and we get CFM. So we want 800 feet per minute. Simple enough. 9.25 average ceiling height, 49-foot interior dimension. Do some math. Okay, boom, 326,000 CFM. Okay. How many fans? We're going to use some 52-inch high-capacity fans. There's a CFM. We're going to design, let's say 0.1 pressure, 27,300. Take 362 divided by 27,300, and we come up with 13 fans. Ventilation system design, time to go home. How much pad area? We take our total CFM at a 0.05, 0.1, whatever you feel like doing, divide it by 350, because we need 1 square foot of pad for every 350 CFM, 375, whatever you want to work. Do the math. 378,300 divided by 350 is about 1,100 square feet of pad. Divide 1,100 square feet times 4.7 foot average pad height. It's not really a 5 foot pad when you put the cover on it and all that stuff. We come up with 230 linear feet of pad. 115 feet per side. Oh, let's round it up and give it 120. We have our 13 fans. We have 120 feet of pad per side. And this big 50 by 560 with 800 feet per minute airspeed. Would we actually get 800 feet per minute? And if we don't, why? And that brings us to what we've been doing for the last 2 years, our tunnel ventilation system performance study. The purpose of the study for the first time is to really examine the factors that affect airspeed and bird cooling in a house, because bird cooling is all about airspeed. And we want to really understand how airspeed changes in a house and what factors affect airspeed in a house. How do we do it? The biggest problem in the past when we're measuring air velocity, we stand with an air velocity meter and say, yep, 800 feet per minute. Yep, 700. Now, with this setup, we have 15 anemometers. We have three anemometers per pole, 5 poles. So we know the air velocity measurements in 15 locations. We're measuring at 2 feet from the floor, 2 feet from the ceiling, and halfway in between the two. They're hooked up to a computer data logging system, and we know the instantaneous average airspeed. We're taking a measurement every minute, or an average over every minute, and we're doing it at 10 to 20 minutes. So we're letting this thing run for 20 minutes with so many fans on. We know the air velocity at every location, average over every minute, and we have some pretty rock solid numbers. We can vary the number of fans. We have different tunnel openings. What happens when you close your tunnel door a foot? Does it affect airspeed? What happens when you use just tunnel fans on the sidewall versus the end wall? What happens when the pads are wet versus dry? How does it really affect airspeed? We're also measuring static pressure, not just in one location, but all sorts of locations. We have done this in over 2 dozen houses, broiler, pullet, layers, broiler breeders. And for the first time, these 15 anemometers allow us to accurately analyze what's happening in these houses. Number 1, determine how the air velocity changes across the profile of a house. Here's again our 50 by 560 foot house. There's your measurement. Oh, it's an 800 foot per minute airspeed house. No, it's not. That's the centerline velocity. That's the highest velocity. If you think about it, do you really want to know what the highest velocity is in a house? You really want to know what the lowest velocity is. But you see the profile here. We actually look from floor to ceiling. Highest velocities are right in the middle, about 5 foot off the floor. Second highest next to the ceiling, the lowest at the floors. Put birds in the house, that drops another 100 feet per minute at the floor. You know what's interesting? It depends whether the chickens are standing up or sitting down. When the lights go off at night, the chickens all sit down, the airspeed at the floor level jumps up 100 feet per minute. Why? Because it's a nice, smooth carpet of chickens. They all stand up, air velocity at the floor drops. Wall-to-wall airspeed. That's the profile across the width of the house. Sidewall around 700, middle around 775. It's actually very uniform. You can determine how this profile changes with the number of fans operating. If I shut off 2 fans, do all the birds receive less cooling? Does it stay the same? How does profile change in a broiler breeder house? This is a broiler house with smooth walls. This is a broiler breeder house. Quite the difference there, isn't there? You know these breeder houses that say have 500 feet per minute? No, they don't. They have it in the scratch area because that's where they measure it. Where is the most important spot to measure air velocity in a broiler breeder house? On the slats. If you want a quick and dirty rule, the airspeed on the slats is half that it is in the scratch area. You have 500 feet per minute in the scratch area, you have 250 feet per minute on the slats. That's the way it works. The air does not want to flow down this area here. Air is always going to take the path of least resistance. Where's least resistance? Right down the middle. 588 feet per minute. These people were proud of this house. Where's the most important? Over here, 344. Oh, how about a high density commercial layer house? 2 stacked cages, upstairs, downstairs. 180,000 birds, straight pool tunnel house. No pads, fan opening on this end, fans on the other. That's its velocity profile across the width of the house. Middle, these are the outside aisles, middle aisle. Highest velocities are actually out towards the outside aisles. Why? Air would rather flow down that than that. Path of least resistance. Where the air really wants to go is up along the ceiling. But this outside aisle actually has great airspeed. Again, we can determine how the profiles change with the number of fans operating. Okay, here it is. That 50 by 560. Here's the air velocity with 13, 11, 9, and 7 fans. With all the fans running versus 7, it stays the same from the center of the sidewall. So I know when I shut off 2 fans, all the birds receive a little bit less cooling. If I shut off 4, they receive all less. Everybody gets the same amount of airspeed as the fans decrease, or the same amount of decrease. Broiler breeders, very different. With all the fans running, look at this. I go from 6 to 9 fans, I increase my airspeed 150 feet per minute. So when I have 6 fans running and I go to all the fans running, the birds in the middle get an additional 150 feet per minute airspeed. They really benefit from turning on more fans. Sidewalls, they only get 50 feet per minute airspeed. Whether there's 6 fans in that house or 9 fans running, they only get another extra 50 feet per minute airspeed. It's essentially the same. The higher the airspeed, the more the air wants to avoid an obstruction. The more and more fans you put in that house, guess what? The more the birds in the middle of the house benefit, and really the birds in the sidewalls don't. Air wants to take the path of least resistance. And these is what we're really worried about, not these suckers in the middle. So you get this type of thermal image. There's the scratch area, warm. There's the sidewall. Airspeed equals cooling. And when I have half the airspeed on the sidewall, I get only a quarter of the cooling. What is the air exchange rate in the middle of the house? It's a 500-foot house. I have 600 feet per minute airspeed. That air is exchanging once a minute, right? What's the air exchange rate on the slats? Once every 2 minutes. Guess what? The air on the slats is going to heat up twice as much as it does in the scratch area. What about forced air furnaces on the sidewall? That's an obstruction, isn't it? This is a 50-foot wide house, that same 50 by 560. Yep. Middle of the house, 750, sidewall next to those furnaces. All along the sidewall next to the furnaces, you're losing 200 feet per minute airspeed. Air taking the path of least resistance, and running furnaces down the sidewall isn't a good thing. Whether it's raised high or low, it's an obstruction. And air is going to avoid the obstruction. As it moves down that wall, it hits those furnaces and moves over to the middle of the house. Here is a 50-foot wide with furnace on the sidewall. There's a 40-foot wide with tube heaters. It is uniform from wall to wall. I have uniform cooling. That's really what we're looking for. Do all the birds receive the same amount of cooling in that house? No matter where they are, we want uniform cooling. That was the problem with our naturally ventilated house. We put a circulation fan out in the middle of the house. These birds received cooling, those didn't. The reason we build a tunnel house is not only to get the airspeed and get it efficiently, is to make sure that all the birds are receiving the same amount of cooling. The grids help us to determine where the best place to measure air velocity. There's our grid. You know the best place to measure air velocity in most houses is about 5 to 7 foot off the sidewall. Now, I remember one of our poultry companies, they came up with this plan that they're going to measure air velocity. All of our houses are supposed to have 600 feet per minute. And they had a plan to measure it 5 foot from the sidewall, 5 foot from this sidewall, and then in the middle of the house. They went and measured their farms, the air velocity was too high. So what did they do? I mean, too low. What did they do? Instead of measuring it 5 foot off the sidewall, we're going to measure it 10 foot off the sidewall. Oh, their house has met the specs. If you really want to know your true airspeed, come 5, 7 feet off the sidewall, 4 or 5 feet off the floor, measure it there, boom, and that's pretty much the closest thing you're going to get to an average. Yes, you can measure it all over these places, but the fact of the matter is what we've seen in these dozens and dozen houses, this is the closest air velocity to the average. The center line will be 15 to 20% higher than your average. So you could just measure your center line and multiply it times 0.8, and that will give you a rough idea. Or again, you could take 15 anemometer measurements for 20 minutes and get the same thing. Okay. This is one of the favorite things I love about this study, is it allows us to answer questions about how tunnel fan placement affects fan performance and airspeed distribution. Fans in the corners. How many of y'all think that putting fans in the corner makes a difference? Better yet, how many of your customers believe that you can't put fans close together in a corner because it affects their performance? We did a study on that. 66 by 600 with 23 54-inch fans. Average airspeed around 800 feet per minute. This is probably one of the highest air velocity houses we've measured. 23 54-inch high capacity fans. Lots of fans. So we ran in the house in this configuration. All the fans in the end wall and those two in the side wall versus all the fans in the end wall versus these fans there. You think by moving the fans out of the corners, I should move more air. What did we find out? Fans in the corners, fans not in the corners, 448, 453. Guess what? Putting fans in the corners does affect the performance. 448 versus 453. 5 feet per minute airspeed. Quick, long story short, it reduces their performance by 2%. Not all the fans, just those 2 fans. So yes, putting fans in the corner reduces the performance by 2%. Not a big deal. How about fans in the end wall versus fans in the side wall? You run into this one overseas all the time. Well, this has to be better than this because the air is coming straight down the house and it doesn't have to turn. Fans in the end wall, fans in the side walls. No difference. If we were pulling the air down the house at 2,000 feet per minute, it would make a difference. We're not pulling the air down the house at 200 feet per minute. 5, 6, 7, 800 feet per minute from an airflow standpoint is not a high airspeed. And the air doesn't have to really hurt itself much by turning. What about airspeed uniformity? This is wall to wall. Fans in the side wall versus fans in the end wall. Doesn't change the profile in the house. The air doesn't know where the fans are until it gets to the fans. So whether the fans are in the side wall, end wall, the air flows down the same. How about this? What if we put all of our fans on one side wall? And we measured our airspeed from wall to wall right there. Would there be a difference? No. Whether the fans are in the side wall, end wall, all side wall doesn't make a difference. Now, granted, we're measuring the airspeed here. There would be a bad corner here. The fact of the matter is, whether it's a high-rise house, how many thought about this? Oh, it's a high-rise house. I have to put the fans upstairs and downstairs? It doesn't matter. The air does not know where the fans are until it gets within about 30 or 40 feet of the fans. So whether we're talking a broiler house, where all the fans on the end wall versus the side wall, the air goes down the house, it gets to the fans, then turns, put them in the end wall, side wall, it doesn't matter. High-rise layer house. Put them all upstairs, downstairs. It doesn't matter until you get to the last 30 feet of the house. And then the air starts to go find out where the fans are, essentially. The other thing it does, allows us to accurately determine how air velocity changes in fan operation. We get these neat little curves. 3, 5, 7, 9. You notice it's not a straight line, is it? I'm going to be talking a lot about that. It tends to be a curved line. The more fans you add, the less airspeed you get with each fan you add. Just the way it works. Last but not least, we can actually, in a house, determine exactly how much air those fans are moving. Well, not exactly, within around 2 or 3%. Because if we know our velocity, we know our area, we know CFM. So here it is, all our fans operating, that's how much air they're moving. Divided by the number of fans, this is their CFM. 3 fans running, they're moving around 28, 5, 29, and then it drops down. We look at our best labs data, guess what? Our field data matches up with best labs data, so we know we actually are doing a very good job of measuring average airspeed, distribution, and CFM. Okay. Getting back to the 50 by 560. With all those 13 fans and 120 feet of pad on each side of the house, this is our airspeed. When we had 13 fans running, we were running 675 feet per minute. What were we supposed to have? 800. We're supposed to be way up there. We did all the math. We calculated it all out. You said 800, Mike. You only gave me 675. Trust me, 675 is good, but 800 is what I paid for. So what's going on? Well, with all the fans operating, we measured the static pressure. At the controllers, a 0.135. At the tunnel fans, it's a 0.17. Obviously, we don't have enough pad in the house. Maybe. Oh, then we measured pressure all over the place. We measured our pad pressure. That's the amount of work required to pull it through the pad. Then we measure it standing at the tunnel door. Then we measure it at quarter house, half house, past the half house curtain, 3/4 house, and back by the tunnel fans. What do we find out? This. Here's the pressure at the pad. As we went down the house, the pressure kept on building and building and building. The closer we got to the fans, the higher the pressure. Why? Sort of forget about wintertime ventilation. And just for a moment, when you think of a tunnel house, static pressure is basically just a measure of how hard the fans are working. That's really what you're measuring. You're measuring work. How much work it takes to get from outside to where you are standing inside. That's what pressure is. So, when we measure static pressure in the center of the house, when our little control room is sitting in the middle of the house, what does that pressure mean? That pressure is the amount of work it takes to go from outside to where we are standing inside, which is halfway down the house. So it's the amount of work required to pull the air through the pads, then through the tunnel doors, and then into the cross-section area of the house. Each of those things is work for the fans. And then halfway down the house. Again, each action requires work measured in pressure of the fans. So it takes 0.04 inches of water column just to pull the air into the pads. Then to pull it through the pads and the door, we have to go through the pads, the 4, plus we have to pull it through the tunnel door. We picked up 2 points of pressure pulling it through the tunnel door. Why is that? We had a 40-inch tunnel door and a 5-foot-tall pad. That causes more work. If we had a 5-foot tunnel door and a 5-foot pad, it would have been less work. Look at that. Quarter house. There's the pads, here where I'm standing right there, and the pressure jumps up to 12 points. What is that right there? That's the transition pressure, which we never used to think about, and I'll show you why later on. You have to keep in mind, on these new houses, the pad area is much larger than the cross-sectional area of the house. 20 years ago, the pad area was equal to the cross-sectional area of the house. But now, we're taking 1,000 square feet of pad area, air coming through 1,000 square feet of pad, and cramming it into a 450 square foot pipe. What does that take? That takes work. Oh, quarter house, just moving it 100 feet or so, took another 1-2 points of pressure. What kind of work is there to go from quarter house to half house? Pipe pressure. These aren't really tunnel house, they're pipe house pressure, tunnel, ventilation house, or whatever you want to call them, because that's really what they are. Whenever a fluid flows down a pipe, there is a resistance or friction. In water pipes, little equation here, we use the old PSI loss value times the pipe length divided by 100 to find out how much pressure loss or how much work it takes to move it down a pipe. There it is. This is the amount of pressure loss or the amount of work per 100 feet of pipe length at different pipe sizes and different flow rates. So if we want to know how to size a pipe or a pump, we have to figure out how much work the pump is doing. And one of the things we have to look at is how long the pipe is. So, how much work does it take to move water down a 500-foot long, 1-inch PVC pipe at a flow rate of 5 gallons per minute? Here we are, 0.8. For every 100 feet that water moves down that pipe, it's going to take 0.8 psi. Or we're going to lose 0.8 psi to move it down there. So, 500 divided by 100 times 0.8 is 4 psi. So if I have 40 psi at my well, at the end of the pipe, I'm going to have 36 psi. Okay, that's pipe flow. Something we never had to worry about before. But with the modern house, the things we're seeing, we're having to start to worry about this. So a tunnel ventilated house, if you think it, is basically a pipe, same laws of physics apply. There you go. This is based on the work we did. We know for your typical drop ceiling, totally enclosed broiler house, turkey house, doesn't really matter, this is how much pressure gain for 100 feet of house length. At 400 feet per minute, 0.0035 per 100 feet. To move air down a 500-foot long house at a flow rate of 500 feet per minute, how much work is required? 500, that's 0.006 per 100 feet. 500 divided by 100 is 500 times 0.06, 0.03. So we know to move that air down that house at 500 feet per minute, we're going to gain 3 points of pressure. You're going to see in a moment why this is important. Oh, then we measure the pressure behind the curtain. It bumps up a little bit. Why? Because that's the resistance. More pipe pressure. By the time we get to the fans, we're sitting at a 0.17 pressure. That's the only pressure that counts. The pressure measured at the fans. That is what we have to design our fans on. Not at a 0.05, not at a 0, not at a 10, but at a 0.17 pressure. Because that is the operating pressure for this particular house. The airspeed was lower than we predicted because we used too low of a design static pressure. We're supposed to be designing at a much higher pressure. Does this large of a pressure, change in pressure, occur in all houses? No, it really only occurs in our high air velocity houses. This is due to a little law of physics. Here's your physics lessons for the day. And I do not have Daniel Bernoulli to come on in here and give a talk on this. You're stuck with me today. And this is so important that it really has a huge impact on everything related to poultry houses. Pressure increases with the square velocity. Okay, what does that mean? If you double the velocity of a fluid in a pipe, be it air or water, the work required to move that fluid through the pipe increases fourfold. Increasing your airspeed from 350 feet per minute to 700 feet per minute quadruples the amount of work the fans are going to be doing now. Oh, it's just 2 more fans. No, it's 4 more fans. How about water flowing through a pipe? We run into this problem all the time. People build these big old houses and they're used to, 1-inch line running down to my cool cells. No, your cool cells are using twice the amount of water they used to. Why? Because you have twice the fan power in the house that you used to. So, 5 gallons per minute, 1-inch pipe, 0.8 psi per 100 feet. We've doubled the flow rate to 10, 2.7. Close to a 4-fold change in pressure. Look at that curve. That is pressure velocity curve. It's exponential. It's not linear. So, 2.7 times 5 is 14 psi. So before, we came in at 40, 5 gallon per minute flow rate, went out at 36 psi. Now, we're only at 26 psi. What does that mean to that house on that nice hot summer day? Those float valves, which are generally undersized anyways, now can't keep up with it, because they're designed to operate at 40 psi, not 20 psi. What a 90-degree elbow. It works. For instance, the pressure required to move water through a single 1-inch PVC 90-degree elbow at 5 gallons per minute is 1.5 psi. Go to 10 gallons per minute at 6 psi. Oh, we were just doubling the airspeed. Just double this. Nope, because of that. How about the filters? Double the flow rate from 5 to 10 gallons per minute. The pressure drop, or the force required to pull water through that pipe or the filter, or push it through the filter, goes up 4-fold. What's that? That's a filter. You double the velocity through that filter, you quadruple the pressure. This is what we do. Okay, 350 feet per minute, 0.05. What if we tried to pull the air through the pad at 700 feet per minute? 0.18. You don't double it, you quadruple it. In the past, low speed, air speeds were relatively low, so static pressures were low. First, the airspeed through the pad was only 350 feet per minute. Minimal work, minimal pressure. 0.05 pressure drop. Then, the pad area, like I said, was equal to the cross-sectional area of the house. What does that mean? Minimal transitional pressure. This is the transitional curve. If I have an airspeed of 350 feet per minute coming from going down the house, I only have a change in pressure of about 0.01 whatever. So at 400 feet per minute, 0.02. So to pull it through the pads with a 0.05. To pull it into the cross-section area of the house, not a big change in pressure, 0.02. Because again, the pad area was equal to or close to the cross-section area of the house. So we had a 5 to pull it through the pads, plus another 2 to pull it in the cross-section of the house. We're at a 7. No big deal. Pipe pressure. This is it. See, the pipe pressure is really low compared to the transitional pressure. 400.0035 per 100 feet. 0.015, do the math, 0.085. There it is. Now, that's what we always design our house around, 5.8 or 5.10, something like that. Everything was wonderful. Here's a question. Is the pipe pressure higher or lower in this house? The work required to pull it down this pipe is easier or harder than a broiler house? Harder. It's 3 times harder. So that pipe pressure you're looking at here, it's 3 times that in a broiler breeder house. Bonus question. Commercial layer house. Someone's read the notes before. It's 5 times harder. For every 100 feet at 400 feet per minute airspeed, I'm going to take about 2 points of pressure. That's why almost every commercial layer house runs at a pressure close to about a 0.20. Just because it's hard to pull air down that pipe. Now, modern houses. How have we solved the pressure problem? We've just added more pad. Because it's the pad that causes the pressure. Therefore, to keep the pressure down, we just keep on adding pad. It's not the pad that causes the pressure. The pad pressure is low because we just add pad, 4, 5 points. But what happens, all these other pressures are increasing. We have a high transition pressure, high pipe pressure. For example, 40 by 500 foot house with an airspeed of 700 feet per minute. Pad pressure, 0.05, because we're still designing at 350 feet per minute. So again, it comes to the pad slow, we're good. Transition pressure, 700 feet per minute. We have to add to that 0.06. The pressure required to pull it into the cross-section area of the house is bigger than the pad pressure. How do you get rid of that pressure? You can't. Pipe pressure, 700 feet per minute, 0.012. 4 divided by 100, because we have 100 feet of pad, so we don't have to worry about that part of the pipe. 4 divided by 100 times 0.012 is 5 points of pressure. So to pull it through the pad is 5 points, but pull it into the cross-section area of the house is 6 points. Then to pull it down the house is another 5 points. All comes up to about a 0.16. Best case scenario. So it actually starts making sense when you start looking back in the years. In the old days, 400 to 500 feet per minute airspeed, we designed our fans around a 0.10. Worked well. Everything worked out, everything's great. But notice what this pressure does. As we go from 5 to 6 to 7, look how much that pressure increases. It's an exponential increase in pressure. It gets harder and harder to get those airspeeds as we try to keep on getting them higher and higher. And it takes special fans to do that. This is for a smooth wall house without tunnel doors and clean pads. Realistically, from a design standpoint, you really have to add a point or two of pressure to that to come up with the real pressure. So if you're looking at your true design pressures for these houses, when we're getting up to 600 feet per minute, you really should be sizing it at a 0.15, 700 about 0.18, and if you want that 800, about a 0.20. Houses that have an airspeed of 800 feet per minute, regardless of the pad length, will have pressures of around 0.20. What's interesting about this work on a brand new house, I can pretty much tell your airspeed just by knowing what the pressure is. I don't have to measure it. Someone says, Mike, I got this brand new house, I measure my pressure back by the fans, and I have a pressure of 0.10 and an airspeed of 800 feet per minute. No, you don't. It's impossible to get the combination of those two. Either your pressure measurement's wrong or your airspeed measurement's wrong, one of the two. Because if you really did have an airspeed of around 800 feet per minute, that pressure would be 18, 19, 20, somewhere in that neighborhood. High airspeeds equal high static pressure, and there isn't anything you can do about it. I love to see house design specs. We want 800 feet per minute, a static pressure of 0.1. Can't get it. Laws of physics say it's impossible. Can we just add more pad? Adding pad will actually do very little good. To decrease the static pressure by just 1 point, you've got to increase your pad area by 15%. Instead of 100 feet of pad, now we need 115 feet of pad. And all that gets us is 1 point of pressure. So instead of having this, we drop this one down, and it drops the rest of them down 1 point. Maybe still more pad, but it really is not going to have an effect on what the work those fans are doing. Here's a good one. What would happen to airspeed if you took the pads out of the house? How much would the airspeed increase on the typical house? This audience participation. 100 feet per minute? 40 by 500 foot house, 600 feet per minute airspeed. With the pad, we're getting right at 600 feet per minute. Good house. And now we're going to feed the world. I guess. Well, thank you, Evan. Oh, there we go. Took the pads out. We gained 25 feet per minute. Pressure went from a 12 to a 9. Even taking the pads out of the house, we only dropped the pressure 3 points. And you look at any of your fans, dropping the pressure 3 points doesn't make a huge impact on their performance. So getting rid of the pads entirely, we only got 25 feet per minute. So it sort of makes sense. Adding some more pad isn't going to really drop the pressure that much because why? It's not the pad that's the issue. It's just the fact that you have high air speeds now. And the other problem, of course, is what are we looking for? We're looking for uniform airspeed. The longer I make that pad, the bigger the dead spot becomes. You think in a house that's 500 foot long that has 100 feet of pad, 100 feet of that house is not tunnel ventilated. 100 feet of that house is cross ventilated. Low air speeds, low bird. 20% of the birds in that house, roughly, aren't really being cooled. 40, that's a 54 by 560 with 5 foot tall pad with curtains. It's 92 feet of pad. Measure the air velocity 20 feet from the sidewall. So all it is, we measure the air velocity here, 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 down with another set of air dynamometers we have. What do we come up with? Here's the fans. There's the end wall. You're looking at how much of this house, half the pad area, 50 feet is right in here. We have airspeeds below 300 feet per minute. Up at the end wall, the first 35 feet, we're down to 200 feet per minute. The rest of the house has 600 plus airspeed. Dead spot. Even when we put tunnel doors on it, it doesn't fix it. 60 by 600 foot house, 110 feet of 6 foot tall pads. Here's the fans, there's the end wall. Down here at the end of the pad, we're running 700 feet per minute up in here. You can see that drop off in airspeed. It's almost exponential. That's the way it works. 300, all that. It has tunnel doors on it. Doesn't really help. Tunnel doors improve the situation. They do not solve the problem. Okay. How do tunnel doors affect airspeed distribution? Again, neat what we can do with this, all this, our fun toys. This is a smooth wall house. This is, I forget what it is. 60, this is at 60 by 600. Or 60, yeah, 60 by 600. I want you to look at something here. This is the air velocity distribution 80 feet from the tunnel fans. Look at your wall-to-wall airspeed. It's uniform. We have a little bit of a peak in the middle, but from sidewall to sidewall, whether we're running 18, 16, 14, 12, 8, 6 fans, it's very uniform. Ooh, there's a variation. Our variation is less than 100 feet per minute. That's pretty dang good. Whether we open the tunnel door all the way or we close it, it doesn't change the distribution. Just having tunnel doors on the house does tend to improve distribution. Why do we know that? Because we tested this. We tested this one because the original claims were that it increased airspeed. That this is better than that from a summertime standpoint. I really wasn't interested in wintertime at that point. So it's a neat little shutter. It's a neat idea. These rotate and pivot just like a fan shutter, and they put on the outside of the house, and they just close them. They don't hang into the house. You know, they're outside, insulated, et cetera, et cetera, et cetera. So we were looking at this going, okay, this is going to improve airspeed. Why, I'm not sure, but that was the claim originally. That's the house with those shutters. Notice the difference from the other house we had? We had this. Look at that. Look at that. Oh, look at that, Mike. This house has 900 feet per minute airspeed. Yes, center line. The sidewall was 650. The average was the same. Distribution. And that happened no matter how many fans were running. Then what do? We partially close these things to this position. The more we closed them, the more uniform it became. They're really not tunnel doors, they're tunnel inlets. Inlets are designed to create an airflow pattern, whether we're talking wintertime or summertime. By getting the air when it comes in to do a rotational pattern like that, it helps to carry it down the house. Now, the sidewalls have to be smooth to keep that profile. If the sidewall has a bunch of posts on it, the air will spread back towards the middle of the house or move towards the middle of the house. But we close these sidewall shutters 20%, we got uniform air velocity. So it tends to prove the airspeed uniformity throughout the house. Tunnel doors, getting that air, tunnel doors, tunnel inlets, tends to get that air going and circulating, and we get a more uniform pattern. Tunnel curtains actually can do it too. The difference with tunnel curtains is you've got to close them a lot to get that pattern. This is a 60 by 600 foot with tunnel curtains. Notice the difference in velocity? So it's almost the same fan power as some of the other houses. 1,000 feet per minute airspeed. I got a 1,000 foot per minute house. No, they don't. You have to average it with the sidewalls, ceiling, and floor. This was the 5.5 curtain opening, 4.5, 3.5. If you think about it, quick and dirty, in order to get the same airflow pattern, I had to close that tunnel curtain halfway. Because what you're trying to do here, so go all the way back, there. What we're trying to do is to close this up enough to create a pattern that the air can go across the house and come back underneath. That's the key, is the air has to be able to come back underneath it. So this air all has to be up towards the ceiling in order for the air to come back underneath. A tunnel door, that's very easy to do. A tunnel curtain, you really have to close them a lot to have that same type of inlet effect. Here you go. Do you have to have a 5-foot tunnel door and a 5-foot pad? Nope. We get into a lot of these troubles because we do rules of thumb. When in doubt, make it the same size. But a lot of times what happens is we never really did the research to say you have to have that much opening because we didn't have the right tools to be able to do that. 50 by 500 foot house, 600 feet per minute airspeed, 92 feet of 5-foot tall pad with a 5-foot tunnel door. Here we are. This is the pressure. We'll look at here. We have pressure at the pad, pressure at the tunnel inlet, pressure at the fan. Really what we're interested in is tunnel the fan in right there. Here we are with a full opening. And what I want to show you here is the total pressure the fans are working against. Going from a 54-inch opening down to a 32-inch opening only changed 2 points. So you can actually have a 5-foot pad on this house and actually close it down to a 3-foot opening, and the pressure only changes 2 points. How much does 2 points, going from a 17 to a 15 or 15 to 13 or whatever, how much is 2 points really going to hurt you? Here's your airspeed. Pressure, airspeed. We lost 20 feet per minute. Because it's not the tunnel door that's causing the problem. 2 points of pressure, okay, you have to know about it, but it's not a killer if you don't have a 5-foot opening on a 5-foot pad. Change in performance, 0.12 versus 0.15. 1,000 feet per minute, do the math. 1,000 CFM, do the math, turns out right. 60 by 600 foot house, 600 feet per minute, 110 feet of 6-foot tall pad, 5-foot tunnel door on a 6-foot pad. Pressure, down to a 36-inch opening, goes from a 13 to a 15, about 2 points of pressure, and our airspeed goes from 560 to 585. Or 600 to 585, 20 feet per minute. 46 foot wide by 560 foot, 565, 700 feet per minute. 110 feet, 5 foot tall pad, 5 foot tunnel door, 5 foot pad. Dome. 0.16, 0.18, 706, 696. We're going to talk about this in a minute. One thing that makes this possible is what? The most important piece of ventilation equipment in there, from a summertime standpoint, is the fan. You put a good fan in there, you can do about anything to it. You couldn't have done this 20 years ago. Our fans weren't any good. But the fans that you and everybody else is manufacturing are so much better than they used to be. Where we used to have to worry about 2 points of pressure, oh, big difference. The rules have changed. We've got better fans. 2 points of pressure, 5 points of pressure doesn't mean now what it used to do. Again, 1 or 2 points pressure does not make a big difference on the air moving capacity of a quality fan. The question is, what are you getting for those 2 points of pressure? Okay, I'm going to give you 2 points of pressure, but we're going to reduce our cost by $2,000. Okay, that's a decision, economic decision. Here you go. Sorry for this one. Do some of our houses have too much pad? The fact of the matter is they do. They really don't need the amount of pad we're putting on these houses, especially the new houses with all the fans and all that. And remember, we used to have a square foot of pad for every 400 CFM. Take your CFM divided by 400. Then we went to 375, and then we went to 350. Was there really a reason for that? Not really. Safety margin, which is fine. But safety margins cost. And it's all about return on investment. Again, increase to 375, then to 350. Now some people are using 325. Why? We got to get the pressure down. You can't get the pressure down. You've got to put in a fan that's capable of moving the air under the pressure you're designing it for. As a result, pad area has increased by about 15% or more on most houses from what we used to do. Add to this that we used to base our pad area on an operating pressure of 0.05. But the fans aren't running at a 10, they're running at 18, which means we're moving less air, which means we actually need less pad. Is this really a benefit? And again, these big old houses are sort of interesting to look at. Because again, this is sort of the future in the US. Not too many people are building 40 by 500 foot broiler houses, turkey houses, or any of that stuff. Everybody's building the big stuff. 60 by 600 foot house, 805 per minute airspeed, highest airspeed house we've measured before, of any we measured. Again, 23 54-inch fans. 60 by 600, 21 52-inch pads, fans, 27,000 at a 0.05. Do the math, 27,000, 21. That's 581, half a million CFM. Our original tunnel houses really had about 140,000 CFM on a good day. 1,662 square feet of pad, divided by 350. 271 linear feet of pad, 136 feet of pad per side. So what we're going to do is we're going to take our 21 fans, 124 feet of pad on each side wall, and then we're going to put some on the end wall to come up with 136 feet of pad. 136 feet of pad on each side of the house. That's all the pad, 805 feet per minute airspeed. That's the front pads closed. We took off all that pad on the end of the house. Airspeed went from 805 to 800. That's not a difference. We took off all that pad, had no effect on airspeed. Because what's interesting, this is the pressure at this end of the pad. That's the pressure on that end of the pad. The pressure goes down as you go down the pad. This is the big reason you can't measure pressure on the end wall of a house. It's going to say, oh, pressure is a 3. What's the pressure really in this house? An 18. So think about how much air is coming through this pad. There's a big pressure difference, so there's actually a lot of air coming through this pad. There's not much air coming through that pad. At a 0.14, the air is coming through that pad at 600 feet per minute. The other end of the house is coming through 250. Long story short, I'm pulling twice the amount of air through every square foot of this pad that I am that pad. So what does that mean? I can get rid of that pad and it won't make any difference. Because really, no air is coming through it. Which begs the question, are these pads really necessary on the end wall of a house? Okay, here we are for the air speeds. These are the front pads in use. This is the side wall. There's the end wall, 287, 207, 61. That's right in the middle of the house. 323, 239, 363. There's that really bad dead spot right there. Front pads in use, front pads covered, use, covered, use, covered, use, covered. Anybody see a difference? If you do, you're better than I am because I can't see it. Is there some difference? Yes. Is it significant? Actually, one of the things we saw is this, when we played with some of this end wall is actually right where the tunnel door is, right over the end wall door. It's actually better when the front pads are covered because this air can go over here and get that air over there. Think about it. If I got air coming in here and air coming in here, and here's my end wall door, this air can't get to there because this air hits it. It acts like a blocking pattern. What if we remove 14 feet of the pads on the sidewall? So we covered the front pad. That's all the pad. Then we covered the front pads. Then we actually covered 14 feet on the sides of the house too. Oh, then why not? Let's cover 24 feet. Covered the end pads and 24 feet down each side of the house, and our airspeed went from 800 to 790. Does it hurt having extra pad head? We want it fine. But it doesn't solve the pressure problem. It doesn't solve the problem that we're going to have a dead spot at the end of the house. What reduces this dead spot is reducing pad length. As I decrease this pad length, I have to pull more air from the pads on the other end of the house. Adding pad just makes the end wall worse. On a lot of these houses, the best way to solve that dead spot, which I'm not thrilled about, put some circulation fans up there. It's realistically the cheapest way of doing it. Reduce your pad area, don't oversize the pad, and then throw in some circulation fans and have at it. But we need to add pad. Come on, we've all heard this one. We need to add pad because when it gets dirty, we have extra pad. Adding pad will not solve the problem when your pads get dirty. When your pads get dirty, whether you have the required amount or 20% extra, it doesn't change the fact. Because if you look at the pressure change from a new pad to a dirty pad at 350 feet per minute, a new pad of about a 0.045, a dirty pad is a 0.075. We're gaining 3 points of pressure when the pad gets dirty. Remember how much pressure a pad we have to add to just decrease the pressure 1 point? You can't do it that way. The only way to help design around a problem of a dirty pad, A, is clean the pad, but more importantly, put a good fan in the house to begin with. A fan that was sized at the right operating pressure, and when the pads get dirty, the fan can handle it. Yes, they need to clean it. But we're not going to get around the fact that a high air velocity equals high static pressure. Determine the number of tunnel fans at the proper design static pressure. Right there. If you want a 700 foot per minute house, size the fans at 0.15. You want 800 feet per minute, 0.20. Have at it. Fan should have an airflow ratio of 0.80. That's a powerful fan. That means as we go from a 0.05 to a 0.20, the fan will only drop off 20%. This is one of the most important design numbers that we've ever had for a high air velocity house. We need a fan that holds up under pressure. Determine your pad area based on the air moving capacity of the fans, of the tunnel fans at 5 below operating. What does that mean? At 400 feet per minute, we designed our fans at a 0.10 and our pad area at the CFM rating of the fans at a 0.05. 500 feet per minute, 0.10, 0.05. 600 feet per minute, size your pad area at a 0.10. 700 feet per minute, size your pad area at a 0.10. 800, size your pads at a 0.15. lots of numbers. We have a much easier way of doing this in a moment. And then install the tallest pad as possible. Work on a distribution system that will fit a 6-foot tall pad on any house. That's the holy grail. Because we only need how much? A 5-foot tunnel door would be fine on it. To be honest, a 4-foot tunnel door would work fine on it. We need to get as tall a pad as possible on that house to shrink that pad length down to minimize that dead spot. Again, this is what I at a minimum want to see is a 6-foot pad and a 5-foot tunnel door. Is there a limit to airspeed that you can maintain in a house? You actually are getting close to it. Where you really see it is in these things. This is, again, the pressure rise in a commercial layer house, high density commercial layer house. Static pressure going down the pipe at 100 feet per minute, per 100 feet of house length. At 600 feet per minute, we're going to gain 4 points for every 100 feet. This is no pads, this is just the house. I have a 400-foot long layer house, and I want to rip air down the house at 600 feet per minute. I'm going to gain 16 points of pressure. Put pads on it, boom, I'm at a 20. This is the house we looked at. This is the curve for this particular house. That's that house I showed you to begin with. These are the number of fans operating. Here we are at 22 fans, but look at this curve. You can see what's happening. It's flattening out. You could keep on adding fans, guess what? Airspeed doesn't go up. You're selling more fans, but the airspeed doesn't go up. It stays the same. CFM per bird. This is one of those numbers that the numbers we're using are sort of silly. Because we traditionally use 5, 6, 7 CFM per bird. You don't need that much. A commercial layer house really only needs about 3.5 CFM per bird. Works fine. The reason we think we have that CFM per bird because we're sizing our fans at a 0.05 and they're running at a 0.20, 0.25. And in reality, you look at our CFM per bird, here is our air velocity, right up here, the airspeed, we're going 450 up to 600 feet per minute. Look at our CFM per bird, it's flattening out too. You can see the theoretical limit is going to be around 3.5 CFM per bird. How do you ventilate one of these? Commercial layer, 3.5 CFM per bird works fine. What about a broiler? A broiler produces about 3 times the heat of a commercial layer does. That's why they're having real fun with these things overseas. You say, I want 6 CFM per bird. You can't get it. I want an airspeed of 800 feet per minute. Good luck. You might want it, but you're not going to get it. So here's the fun part. Upgrades. You know those 48-inch fans we always said move 20,000 CFM? They never did. Even when they're new, they're moving around 17. And we've done a lot of research on this. Is some of the late 80s, early 90s fans. And the fact of the matter is, yeah, at about a 405 pressure, they moved about 16. But the problem is, when we start getting our pressures up, they're basically a good 36-inch fan. That's the problem. Mike, I have 400 feet per minute. All I need is another 200 feet per minute. No, what happens when we add more airspeed, what happens to those fans you have in the house? They move less and less air. So actually, you need an extra 300 to get 200, that type of thing. This is a really good 48-inch fan from the early 90s. Really good fan, 15,000 CFM. So if I'm doing an upgrade of a house, I have to figure, okay, I've got these fans in the house. How much air do those 48-inch fans move? On a good day, you can only really claim them for 15,000 CFM, not 20. Because even though at a low pressure they might move it, they generally don't hold up to pressure as well as our new fans do. They're just a different animal. There's our old fans. This is the new stuff we're doing. Totally different animal than what we had before. Okay. How do you, Mike, okay, all these charts, all these graphs, all these curves, all these things. How do I design a house? How do I know how much pad area affects my airspeed? Now really think about it. You're designing a house and you say, I have 100 feet of pad. What would happen if I put 110? Do you really know what would happen to your airspeed if you added an extra 10 feet of pad? Do you know what would happen to your airspeed if you added one fan and didn't add pad? That's the problem. We don't have any hard numbers. So we want to know how pad air affects airspeed, how tunnel door size affects airspeed. What would happen to my airspeed if I put a 4-foot tunnel door? I know I put something up here and said it doesn't make a difference, but if you want to show something to your customer, how would you do that? How does fan condition affect airspeed? Well, Mr. Jones, see these pads, how lousy shape they are? We need to put new pads in. Well, what would I get for it? Those are the questions that make it real hard. And again, how does conduction of the pads and the fans affect conditioned airspeed? We have a spreadsheet for that. This spreadsheet has thousands of calculations going on behind the scenes. It's based on all the work we've been doing for the last 2 years, and actually before that, on exploring the relationships between air velocity and static pressure. It's actually really straightforward. You put in your house length, your house width, your sidewall height, your peak height, your total pad length, your pad height, your tunnel inlet opening size, and your pad condition. And you put in the fans you want to put in the house. With that information, it will tell you exactly what your pad pressure is, your tunnel door pressure, your transition pressure, your pipe pressure, and your total fan pressure. It will tell you how much air the fans are going to move. It will tell you your total fan capacity and your average airspeed. You can change any of those factors and it will predict within a few percent of what your airspeed will be based on all this work we've been doing with all these anemometer poles for the last few years. You get a nice little graph right here. It tells you your pad pressure, your airspeed, and what the pressure will be in the middle of the house. Better yet, you can add fans of a different type. So you can go to a house with 8 old fans. Okay, Mike, here's the house. It has old pad, old fans. How many fans do I have to add? We can guesstimate it, but we can actually put in the fan performance data for an old fan, add some new fans, and it'll tell you exactly what your average airspeed will be within a few percent. So, here's a house. Again, it's a 50 by 400, 7-foot sidewall, 10-foot peak. We're going to put 70 feet of pad on each side of the house. We're 140 feet. A 5-foot pad height, 5-foot door. We have nice new pad. We're going to put in 9 new fans. These are one of your fans, a 54-inch fan. Tells us what the CFM is, and we say their condition. Boom. Come down here. Pad pressure 0.046, transition pressure 0.035, pipe pressure, add all those up, we get a 0.114. Our fan's going to move 23.8. Average airspeed of 594. Simple as that. Okay, what happened? No, I want to put a 4-foot tunnel door on this. $588. No, what happens if I close that tunnel door up to 3 feet? Nope, wrong one. Notice I get a tunnel door pressure of 0.02, which drops my airspeed to 573. Well, what's going to happen? Go back to this. I'm going to make that 4 feet. What happens 5 years from now when my pad gets dirty? 549. What happens 5 years from now when my pad gets really dirty? 486. Notice look at what happened. My pad pressure went up, but what you notice is my pipe pressure went down. Why would that happen? The pad pressure goes up, which reduces my CFM, which reduces my airspeed, which reduces my pipe pressure. They all interreact, interrelate. And I can go down here, and I can see my pad pressure is really what's driving everything. 0.132, 0.178. So all of this is very doable. So, again, you can change all this, and let's look at a different example now. We have an older house. 50 by 400, 50 by 500 by 40, 7.510. We have 50 feet of pad on each side of the house. Pad height conditions 4. So we have this older house, 500 by 40, 100 feet of pad, old pad. We have 8 fans in. These are the old, probably like an old Acme or Cool Air fan. They're in, we're say condition 3. Our pad static pressure is a 0.064. Our total pressure is about a 0.089. We don't have any really transition pressure. We don't really have a pipe pressure. Our fans are actually moving 15,000 CFM. Average airspeed of 351. Oh my, it's 450. It's 450 in the middle, but if you do a true average, you'll really realize it's 350. Most of our old houses that I've looked at, in terms of what their airspeed is, it's around 350, 400. Now, how do I get my airspeed up? Come over here. This is one of your 54-inch fans. I'm going to put 2 fans in without doing anything. I'm just adding 2 fans. I'm not changing my pad. I'm not cleaning the pad. I'm not adding pad. My pad pressure jumps up to a 0.103. My average fan capacity, that's the average of all the fans, goes to 16. I'm only at 446. Not there. What do I need? I need 600. Well, let's come in here. Let's add 5 fans. I'm still at 543. The more fans I add, what happens to those old fans? They just keep on dying. So you go, no, Mr. Jones, what we need to do, we're going to add 3 fans. We're going to put in some new pad. We'll make our this fan condition is going to stay at 3. Yeah, we're going to put new pulleys on the fans. Get that up to 2. We're going to change this to 180 feet of pad. Too much. Notice I'm looking at my pad static pressure right here. I'm going to get that to about a 0.04. So I can sort of play with that. 160. There we go. Again, I can put any pad length in this house. I don't have to divide it by 350. I can actually design the house. Okay. 8 fans, 3 new ones, new pad, 80 feet of pad on each side of the house, 5 foot tall, 580. Okay. Close. Oh, let's just go with a 6 foot tall pad. Drop the pressure down a little bit, 583. Okay. See the point. You can sit here and play with any combination. Go up to 4. Got to add fans. Get my pad area up to like 180, 90 feet of pad, or 180. Away we go. 644. Again, this is for the first time we actually can design our tunnel ventilated houses. You can put in any number, any of that, and you make the decision based on the fans you put in the house, what you can do. Okay. Got that. Here's 3 of your 54-inch fans. You got to figure out which one to put in. You can use in that spreadsheet, but you got to look at these 3 fans. They're pretty much identical fans. HGS 554, G3, 40, 34, and all that. You all know these numbers, not me. First, for a higher velocity house, which fan is probably the least desirable? That one. Has an airflow ratio of 0.70. What's really not good about this fan, could be a great fan, but from a high air velocity house, notice what's happening. This is called a knee. Look how straight that fan is, straight, 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 and boom, it drops off. Between a 0.20 and a 0.25, it goes from 18,000 down to 10,000. So here you have this higher velocity house, you're running an 18 pressure. The fans get a little dirty. The pad gets a little dirty. The pressure goes up 2 points. What happens to the fans? They go off the cliff. I'm going to put this in a turkey house as a tunnel fog house. I don't have pads. I only have an airspeed of 600 feet per minute. My pressure is only going to be around in here. fine, have at it. There's really nothing wrong with that fan. But the higher the static pressure, the less you want that fan. They all have a knee in them. See this one? Where does the knee occur? At a 0.25. This one, way up there someplace. So, of course you're saying, well, that's the best fan, the 0.81. Yes, it is, but has the lowest energy efficiency rating. High airspeed equals high static pressure, which equals high cost. This fan, you're looking at 18 CF per watt versus 23 CF per watt. About a 20 some odd % difference in power usage. Though this is a good fan in terms of airflow ratio, it's not so good in static pressure. But if I'm designing for a high air velocity house, I'm going to tend to use one of these two fans up here. Anybody know the difference between these fans? Hopefully some of you do. Pulley size. When in doubt, put the 1.5-horse motor on it and a smaller motor pulley, and then later on they want more airspeed, just change out the pulleys. But it has a 1.5-horse motor on it. It will still be energy efficient because it's not being driven at the higher RPMs. A 1.5-horse motor with the same pulley size as a fan with a 1-horse motor use about the same amount of power. It's not until you put the bigger pulley on it and speed it up that it starts drawing more power. So the safe bet is put the bigger motor on it. Hey, it's a safety factor. And if later on they want to say, I want more airspeed, we swap out the pulleys, and you can predict it on the spreadsheet exactly what's going to happen. Pullet houses. These are fun. Because in a pullet house, there's all sorts of restrictions. Not only do we have this restriction, we got that restriction too. How does pad area affect fan performance? We just use these numbers, but we don't really know. What happens if I put a little extra light trap on the house? What happens to airspeed? What happens to our ability to cool the birds? Well, guess what? I've got a spreadsheet for that. We have this one right here. A pullet house spreadsheet. You put in the type of light trap, your house length, width, your peak height, your fan light trap area, your inlet light trap area. If you want to put pads on it, you can do that too. And you put in the number of fans you have over here, and it will tell you all the different little numbers here. So we can go into here. If I can find it, there it is. There we go. So again, you have all these little numbers here. It's sort of involved, but it's the same principle. You've got your fan light trap, what type of light trap, because each one makes a difference, your house size, all that. We have 7 fans. These are the CFM on those 7 fans. All these green values are things you can change. Tells you the total square feet of fan light trap you have, your total square feet of inlet light trap, your minimum recommended area, your light reduction factor, but most importantly, it will tell you your airspeed. Okay, so we have 357. What happens if I go from an Acme plastic light trap to my old favorite, the General Seltzer light trap? 263. Why? Because the static pressure goes to a 0.244. Change the light trap back to the Acme. 1. Pressure drops to a 0.16. Airspeed goes up to 357. Oh, what happens if, let's put cool cell on this thing too. What the heck? Money's no object. We're going to make it, our inlet light trap, we have 60 feet. We're going to go 5 feet. That's your height and length. Add cool cell to it. Pressure goes up to 0.19. Airspeed at 328. So really what we have here, what we've been able to develop with all these neat little toys we have, is a way to really design a house. Up and before we said, okay, we need 1 square foot of light trap for every 750 CFM on the fans, 500. We just had these rules of thumb. We need 1 square feet of pad for every 350 CFM. We had all these rules of thumb, but what we're able to do is actually come up with ways that you can actually experiment for yourself. Well, Mike, what would happen if I put the same amount of light trap on the fan that we have on the pads? On the fans that we have on the inlet. There you go. What happens if I put in twice the amount of fan light trap and half the amount of inlet, or twice the amount of inlet, half the amount of fan? Whatever you want to do, it'll do it. And it will predict it pretty dang accurately. Is it perfect? No, but it's a heck of a lot better than the way we have been doing it. So again, with these two tools, you can really predict what a house will do. Now, the downside is we're still working on the commercial layer one. That's a little bit more involved on how to do a cage system. But the fact of the matter is the pipe pressure is actually accurate, and you can actually get pretty close. And what you're going to find out in a commercial layer house, your pressure is always going to be about a 0.20. That's what you have to plan for. And it's going to take a heck of a fan. And when I'm looking at a 0.20 pressure, that's the fan I'm going for right there. That high static pressure fan. It's going to use more energy, but that's part of the process. Is that if you want the bird cooling, it's going to take the most powerful fan you have. Pullet house, I'm going to use that fan. Layer house, I'm going to use that fan. 800 foot per minute broiler house, I'm going to use that fan right there. Tunnel fog houses, I might be able to drop down one of the other two fans. A retrofit up to 600 feet per minute, I'll use one of the other fans. But again, you can play with all this within the spreadsheet. There we go. Okay, I've done the talking. Now let's hear the questions now. And again, we have a lot of this. The spreadsheets I can get to you. I know you're all feverishly writing down notes. I can get you these spreadsheets. Just let me know. I'll email them out. You can play with them. Some are on the website right now. So you can download it from our website there along with everything else. And just for information purposes, our winter ventilation workshop is coming up the first week of November, November 5th, 6th, 7th. If you're interested in attending, let me know. Or you can go to our website. You can look it up there too. What's the ideal broiler house size? I would say, from a cost-effective standpoint, my ideal would be a 40 by 400 with 600 feet per minute airspeed. You can't do it. But from a cost, performance, operating and all that, probably in the neighborhood of a 60 by 600. I think those make the most economic sense from a heating, cooling, ventilation standpoint. You look at other things, whether it fits in with a processing plant and all that's another question, but 60 by 600, broiler house, turkey house, I think that's a good size. Dairy barns are a lot difficult because the air is, we have all these stalls and everything, and the airflow varies all over the place. When you get in a dairy barn, you almost have to make just multiple measurements and average it. Because it's like a broiler house with curtain deflectors. Trying to measure the airspeed is really hard to do because it's just so turbulent. So when in doubt, you have to make multiple measurements and come up with an average there. But even dairy barns, their pressures tend to be high just because the air is having to go through all sorts of different contortions. And that's one of the reasons they're cross-ventilated. Because the pressure going lengthwise, a lot of them would be really high. Okay, Jackie.
Okay. What is it about the broiler layer function that causes 3 times the bird-heat relationship?
Growth rate. Basically, the faster the animal grows, the most heat it produces. What produces more heat, a 1-pound bird or a 5-pound bird per pound? A 1-pound bird produces like 3 times the amount of heat that a 5-pound bird does. A big turkey, 40-pound turkey. If you look at a turkey in a brooding barn, they're producing about 10 BTUs per pound at about 3 weeks. At a grow-out pound, they're producing about 3.5 BTUs per pound. The older the bird gets, the less heat it produces per pound. The trick is there's just more pounds to deal with. It's all a function of growth rate. When is a turkey, when is a broiler growing the fastest? At the very beginning, and that's where they're actually producing the most amount of heat. The good side, bad side is there's not a lot of pounds in the house, so it doesn't matter. So bottom line, if you look at a breeder or a layer, they're not growing. So therefore, their heat production is a lot lower.
What I'll do is just read the top two or three cards, and if you have more than one question on a card, in order to be fair, I'll just go on to the next card. Do you have a rule of thumb for predicting static pressure based on airspeed through the inlet? Is there a relationship?
The pressure, airspeed, give me 1 second here. Have all the answers here, just have to find them. If you come to the winter workshop, I'll tell you exactly what it is. Okay, winter school, negative pressure. This is the pressure. There. That's pressure difference versus airspeed coming through an inlet. You got the pressure for pads. You know, the pressure curve I showed you, the little curve there, you'll get that. 350 feet per minute, 0.06. At a 0.06 through a plain opening, the air is going to come in at about 1,000 feet per minute. So what does that tell you? A pad is about 3 times more restrictive than a plain old opening is. So again, if I go to a house with just an opening, an inlet, and I got a 0.1 pressure, I should be measuring about 1,200 feet per minute coming through that opening. Go up to, again, 0.20, it will be about 2,000 feet per minute. I use the rule of thumb, it works most of the time. 500, a 0.05 is like 700, a 0.06 is like 800, add like 200 to it. 0.08 is 1,000, 0.12 is 1,400. It works pretty easily that way.
Okay, next one. What difference does it make if you use a shorter cone on a tunnel fan versus a longer cone? What effect does that have on fan performance?
The true answer is you can't tell by looking at a fan what performance is. That's why we have testing. Is that how much a cone affects the fan is a function of RPM of the fan, blade design, and all that. So it's really hard to tell lengthening a cone. That's the long answer. The short answer is probably not much. Probably 1 or 2%.
Okay, can we get the spreadsheet that was used in the presentation that calculates air and tunnel pressures?
Yes, you will. No problem.
One more? Time for one more? Okay. Did you evaluate cooling efficiency with less pad as well as velocity?
The cooling efficiency, give me a second here. Second. Oh, next. It's always a challenge, is remembering exactly where you put all this stuff. When you have 1,000 presentations. Go. Okay. These are cooling efficiency curves. This is the amount of cooling you can get out of a pad at different velocities. The in the typical weather, most pads are capable of producing about 20 degrees cooling if they're 100% efficient. So let's look at this, okay? It's 70 degrees during the day, 70 degrees at night, 90 degrees during the day. There's a 20-degree differential. A pad that's 100% efficient will actually get you nighttime temperature. So if I have a pad, it's 70 at night, 90 during the day. Long story short, with a 100% efficient pad, I could drop the incoming air temperature to 70 degrees. The downside is the humidity would be 100%, and you'd probably kill all your birds. So a rule of thumb that we use, pad efficiency, if you multiply your pad efficiency times the difference between your daytime and your nighttime temperature, that'll tell you cooling. So the typical pad is 75% efficient. So if 70 degrees during the night, 90 degrees during the day, 20-degree difference, the typical pad will get you 75% of that, which is 15 degrees. Okay, follow this. This is the real cooling efficiency right here. At 350 feet per minute, the cooling efficiency of a 6-inch pad is 72%. 20 times 0.72 is 14 point something, okay? If I decrease my pad area by increasing the velocity through the pad to 400 feet per minute, the cooling efficiency drops to 71.5. We go from 73 to 71.5. We go multiplying 20 times 0.73 to multiplying at 0.71. Is there a difference there? No. What's fascinating about a pad, whether you pull the air through it at 250 feet per minute or 400 feet per minute, the cooling really doesn't change. Because the cooling efficiency curve is actually very flat. And that's why you can take a pad to take an inch off of it, thickness-wise, guess what? Cooling doesn't change. Oh, that black coating on the pad reduces cooling. No, it doesn't. Pads are very stable in their cooling. What changes the most as you change airspeed through a pad? Pressure. That's why we put the amount of pad we do on the house we do is not for cooling, air cooling, it's really for pressure. That from a cooling standpoint, we could cut that pad area by 40%. It wouldn't have an effect on the incoming air temperature. Our fans wouldn't move any air, but at least the air coming in the pad would be about the same. So again, that's something that we can add to that spreadsheet. I've been thinking about it just to show cooling when we change pad areas on that. But again, the short answer is it's not going to affect the cooling produced by the pads.
I think we're probably running, we're okay with a couple more questions. Okay. Just how fast can we go in airspeed? How much does that increase the pad efficiency by slowing the air over the pad?
Again, pad area, you can play with it right there. We have another spreadsheet that will do that too. So we have during the winter tunnel ventilation workshop, one of the spreadsheets we have, I don't want to try to call it too much of pain right now, is that you can actually change the pad area and it will tell you how much cooling you get off the pad. So there's spreadsheets for that. The answer is really you're not changing the cooling by adding more pad. You're not changing the cooling by putting different water temperature on the pad. The pad is going to cool what the pad is going to do. The biggest reason, again, the design criteria for pads are pressure.
Okay. Okay. I think actually we're down to one more, but okay. I don't like pad cooling. What are your thoughts on high pressure misting?
High pressure misting, the challenge, I'll be honest, and we have your high pressure misting system on our research farms. You know, and there's certain houses that works great for. A perimeter inlet house, you can't do better than high pressure fog. I'm probably saying sacrilege here. We have more problems than nozzles clogging. Even with our city water, our nozzles clog. And it's okay because we only have 40 nozzles, 50 nozzles per house, no big deal. But think about a house with 500,000 CFM. How many nozzles that's going to be? Off the top of my head, probably 500 nozzles. That's really, to be honest, the only issue I have with high pressure fog. Have at it. It's fine. It works great. Because the fact of the matter is 80% of the cooling produced in these tunnel houses is airspeed. There's a lot of commercial layer houses that don't have any pads out at them all. As long as the temperature stays below 100, they actually do okay. Goes above 100, not so well. Now, if 80% of your cooling is determined by airspeed, whether you use padders, fog, sprinklers, whatever, get the cooling there. High pressure fog, I don't have a problem with it. It just takes a lot of nozzles and it has to be a lot of staging. With a high pressure fog system, in my opinion, you don't put them on a timer. You do a third, another third, another third, and stage them up as it gets hotter and hotter. I think that's the most effective way of doing it. So, again, a high pressure fog, have at it. You really don't have a problem with it. Your pressure is still going to be high if you have the high airspeed. It just comes down to a question, are you going to be able to maintain 500 nozzles in a house with high airspeed? An old house, low airspeed, 100 nozzles, have at it. But just keep in mind, the more fans we add, if we double the fan power, we almost have to double the number. We have to double the number of nozzles, and the numbers get sort of obscene after a point.
Okay. As Mike said, all your questions will be answered. If there were 2 or 3 parts to your questions, you will be contacted. So if we missed anybody, I apologize. And I guess now we're going to have a 15-minute break, right? No? Yes. Okay. So we're officially.
Thank you. Thank you.